Good morning, everybody. I would like to thank you for being invited for this talk. I hope that I managed to interest you in these subjects, or if not, at least that you have a very good hour of sleep. I'll try to inform you about my ideas, the research that I'm conducting here in Brazil regarding biorefineries. I'm going to focus on the what I call development stage and perspectives, because, in my opinion, we are on a verge of a transition. Well, that's of course true because we are transitioning to a renewable energy grid, and bioenergy plays an important role in this area. So, first of all, I'm going to talk about the problem, what I consider the problem. The problem is that we live in a non-renewable carbon-based economy. Since the Industrial Revolution, in order to obtain energy for our processes, which, by the way, is very tightly related to the quality of life, we have been searching for energy from fossil sources, petroleum, coal, and gas. So that's the problem. I'm sure you are aware of that. Do I have a laser pointer here? Yeah, okay. So we're getting energy from fossil resources to drive our processes for elimination, for transportation, and so on and so forth. And we are sending to the atmosphere these atoms of carbon here, which were very nicely, very quietly sleeping underground. So that has an important consequence for environmental concerns, and that's our motto today. Just to give you some number, we are producing more or less 500 exajoules of energy. Exa is 10 to the 18. And this energy drives all of our processes, and also to build chemical compounds, including food, for instance. Food is very important because when we manage to develop machines for agricultural production, which needed power, I mean steam tractors, for instance, that revolutionized completely agricultural production, which enable higher populations without starvation. So that's really revolutionary. So that's our motto today. The solution would be at least to have a non-renewable, if we cannot do otherwise, but carbon-neutral based economy. So we would need, this is just a proposition, we would need to build something like a CCS machine, a carbon capture and storage machine, which of course will need energy to make this, to perform this task. And this CCS machine will have to inject those carbon atoms which were underground. That's one possibility, but I'm going a little bit further. We could build a renewable, neutral carbon economy. I mean, if we tackle renewable sources, biomass, for instance, which is basically solar energy stored in the form of chemical compounds in the plant, if we manage to tackle that at the scales that are necessary, because scale is a very important issue in this context, this emission here, this carbon atom, actually was in the atmosphere. So, in principle, it's neutral. Okay? We can go a little bit further and try to devise a renewable, negative carbon-based economy. What about, this is just speculation. I'm going to show that this is possible. We're making all the calculations to prove that that is really possible. Just a minute, please. Yeah. Okay. What about transforming our biorefineries in CCS machines? If we take a little bit of the energy that this biorefinery is capable of producing and use to capture and produce what we call supercritical CO2, I'm going to explain what's that, which is proper, which is adequate for underground injection. Those are ideas that I'm just showing, and that's more or less the guideline of this presentation. Okay? Try to go from a carbon positive economy to a carbon negative economy. And I'm going to try to emphasize the technological challenges related to these ideas. And biorefinery, bioenergy is certainly one of the most interesting possibilities to make that, because it's a natural CCS machine. But how renewable energies will displace fossil energies? That's one point. Another question, carbon capture and storage technologies can extend exploitation of non-renewable energy sources. That's a very important issue, especially nowadays when we have these shale gas and shale oil technologies being commissioned. So that's a very important issue, a very important question. Sometimes the questions are more important than the answers. And in this context, bioenergy will play an important role in meeting this expectation. Remember I told you, I mean the world consumes about 500 exajoules of energy. What we call the potential biomass energy supply would be 3 times as that, 1,500 exajoules. Okay? That's the big picture. I'm going to focus on biorefineries, and as I said in the beginning of my talk, I'm going to try to elaborate what's the technology maturity level and the perspectives. I mean, transitioning to a carbon negative CCS machine. To talk about that, I need to define what we call an industrial reference unit, because I need to put numbers in these ideas, okay? So let's think about this model. What we call an agro-industrial reference unit is actually some amount of area on which crops are cultivated, okay? This biomass has to be harvested, has to be transported to a central industrial unit, which will convert this biomass into products, okay? Where you have value added here, and you have products. So if you think of that, if you accept that, and this is quite sensible, it's still a speculation, but if you write down all the equations, you see that that's the general behavior. If you consider, for instance, your revenues, okay, I'm going back one slide. Your revenues are proportional to what? To the amount of biomass that you can transform. The amount of biomass is proportional to the area. And if you define a radius R of this area, if you admit that it's a circle with the industrial unit in the middle, so the amount of biomass which is proportional to your revenues is proportional to R squared, okay? So the blue curve is proportional to R squared. Now, let's think about costs, okay? That's the red curve. I'm going back one slide again. Costs are proportional to what? It's proportional to the amount of biomass that you have to process, but also to the distance that you have to transport in order to get to the central industrial unit. So it's roughly proportional to R to the third, okay? It's not coming from zero here, because you have fixed costs related to the acquisition of the equipment. And you see that your revenues are bigger than the costs within a certain scale limits. Why this is important? Because if I'm developing a technology which is not viable within these scales, it's worthless, okay? So that's the point. The viability of this agro-industrial model happens within defined scales, a minimum processing scale and a maximum processing scale. This has profound effects on how these biorefineries will be developed, okay? Those were speculations. We can try to see if this actually is happening. I'm referring now to second-generation biorefineries. I'm going to explain what that means. And this is compiled, all these dots are second-generation biorefineries all around the world, okay? The green dots are in operation. The red ones were abandoned. The yellow ones are supposed to be commissioned in 2014, 2015, okay? So this is, again, this is compiled by the International Energy Agency, and we can make statistics because you have several data related to this project. This is one of the biggest one, Chemtex plant in Crescentino, Italy. It's the biggest one. And actually, one just like this one is being commissioned here in Brazil in this year, in 1 or 2 months. Okay. Regarding a modern second-generation biorefinery, what is claimed is that these biorefineries are already operating within those limits. Okay, that's one point. If you open each of those projects and you see the processing flow rate and all other things, you can make statistics. I made one. That's the processing rate. So this is a histogram of processing rates, 40 tons per hour, 30 tons per hour. That's biomass, okay? And here is just the number of biorefineries, okay? We made a cut. The total here is 105 projects in 18 countries, 59 processing or assessed, okay, with bio and thermochemical conversion. That is, in addition to combustion, you can have pyrolysis or gasification technologies, for instance. And it's being commissioned between 2008 and 2014. So you see the majority of those projects are here, 10 tons per hour. Please bear this number in mind, 10 tons per hour. And the one that I show in Crescentino is actually this one, 70 tons per hour, okay? So it's really big, but my point is it's not big enough. I'm going to show you. So that's Crescentino. Actually, it's a Brazilian company called Bio is associated with Chemtex, and Bio is commissioning one of those biorefineries in Alagoas, not very far away from it. So my point is that if all those projects were commissioned in this scale, 10 tons per hour, my point is that things are not being tested regarding the risks of several things. For instance, agricultural production. At 10 tons per hour, you don't have, for instance, the logistics problem of bringing all this biomass to that central processing point, the industrial unit. I'm going to show you that. I'm going to elaborate on that. Also, feedstock logistics and production. And finally, the economic viability scales, which I emphasized in my last slides. I don't know if you are aware of these, with this technology readiness levels, TRLs. I don't know if you're aware, but basically it's a scale which measures how much a technology is mature, ready for being tested. The first levels are actually the first physical and chemical concepts. I mean, the idea inside the head of the scientist, then he makes some lab experiments to confirm his hypothesis, and then you can make benchtop models, you can make engineering prototypes to test these technologies, and finally you have demonstration plants and full-scale plants. So this is a scale accepted, well, generally accepted all around the world. So what's claimed is that all those projects regarding second-generation biorefineries are already between TRL 8 and 9, which means it's very close to the full-scale plant. I'm going to argue on that. That's what's claimed. And this actually, I'm going back one slide again, is that actually around these processing scale, 10 tons per hour for second-generation biorefineries. So let's see some first-generation biorefineries, which we here in Brazil, we are operating these biorefineries or sugar mills since mid-70s. So this is 500 tons of sugarcane per hour. This is a plant. Okay, you see, I mentioned about the logistics problem. You see the trucks here? You see that they are unloading here, and each wagon here weighs about 40 tons or 50 tons, something around that. And you have to unload. You have 5 minutes to unload each wagon, okay? And this works for 200 days, 24 hours a day. So you cannot have traffic jams here. In order to unload these wagons, you have to be very smart, I mean, in harvesting, in programming when you're going to harvest a certain field of your plantation, when it's going to be brought back to the industrial unit. And you have an additional problem that you have to minimize the time between harvesting and processing, because the plant stops photosynthesizing, so the sugar content is decreasing. So that's an additional problem. And you have to do this, and you have to do these at these scales, which, if you think about the logistic problems, means that you have to unload each of these wagons in 5 minutes, roughly speaking. So that's an average biorefinery, actually. That's a little bit smaller, okay, 500 tons of sugarcane per hour. And that's a big one. It's commissioned two years ago and is designed to operate at 1,000 tons of sugarcane per hour. That's near Brasilia, this one, in the state of Minas Gerais. Those are the scales that are viable for sugarcane in Brazil. I'm using sugarcane as a test case because it's already tested. You have a lot of experience on that, a lot of problems that were solved successfully, so we can use that to try to infer what would be a biorefinery based not necessarily on sugarcane or cane energy, which is another variety of sugarcane, but also on other kinds of feedstocks. But those are the scales that we have to test, or new technologies, or second-generation technologies. Not to test, but to see if they are viable at those scales, okay? My point is that 10 tons per hour, actually, it's an engineering prototype because you're still developing machines and process for the industrial biomass conversion. 10 tons per hour, you're not testing all the problems that you're going to have at those higher scales, and they're going to be even higher if you think about other kinds of feedstocks. 100 tons per hour, which is more or less what Crescentino, the biggest second-generation biorefinery, remember it's 70 tons per hour. It's already a demonstration plant because you're already demonstrating conversion models and scales, allowing extrapolation. And 1,000 tons per hour, you're actually on the game. It's going to be even bigger because, well, there's some photos to what full-scale biorefinery will evolve to in the near future. That's my point, okay? Just to emphasize on one aspect of this problem, the reception and mechanical preparation of your feedstock. This is what is already working here in Brazil regarding first-generation processing for sugarcane. But it's similar for acacia. It's a kind of tree from which you extract tannin, for instance, and other types of biomass. But you have a problem of unloading your truck. You have to separate straw from the stalks. You have to separate sand and dirt, which comes with your biomass, especially if biomass is being mechanically harvested. That's a big problem. And you have this time scale, okay? It really works. I mean, frankly speaking, not the separation. Separation is still a very inefficient operation, but it's a very good opportunity. Roughly, it works. You manage to process each truck each wagon in 5 minutes. In Crescentino, you have 45 minutes to unload because you have bales. Actually, they are working with wheat bales. So part of the processing is done in the fields. which means that it's inefficient compared to a processing made on site, okay? And you have these scales. So you actually don't have these logistic problems. I mean, all those trucks arriving at the industrial unit. I mean, this is so sensitive. Even the geometry of the streets and roads that takes you to the industrial unit is important. There are research regarding how you design these lanes and streets and roads in order to facilitate the flow of trucks and biomass and so on. This is a very serious issue. So my point is that a new technology development cycle will be necessary. Remember, the majority of the projects in the world, all around the world, process around 10 tons per hour of feedstock. And we are talking about, regarding the full-scale biorefineries, processing rates greater than 1,000 tons per hour. Okay? So a new development cycle will be necessary. This is true because it can be observed in practice. There's a lot of projects that are being abandoned or redesigned or re-engineered. Actually, these new development cycles will need these step backs. First, we're going to look to new industrial conversion and processing technologies. Unloading biomass is a very important issue when you work at the big scales, and it depends on the characteristics of your biomass. This is a very important issue. Also, you're going to have to look for new disruptive technologies based on new scientific discoveries. I mean, more efficient enzymes which can be produced at large scales at low cost. Those are some research opportunities regarding the most basic levels and engineering research. And CCS is here. Because remember, in the beginning, I was telling you that we can speculate in transforming our biorefineries into CCS machines. I want to show you how this can be possible, because part of your revenues can be generated not by selling electricity, by selling ethanol or some other biofuel or chemical compounds, but also by selling carbon credits. Okay, if this market really becomes viable, which I think it will because of shale oil and gas. Actually, I jumped to the conclusion of my presentation, but I'm going to come back, okay, and go ahead. So, regarding our industrial biorefineries, that's the point. Possibly 99% of biomass processing will be dedicated to producing energy vectors, electricity and biofuels. And possibly 1% of these biomass is going to be used to produce high-value biochemical compounds. That's from the point of view of processing. If you look from the point of view of economics, maybe 50% of your revenues comes from energy vector, 50% from high-value biochemical compounds, and 50% from carbon credits. It's not summing to 100%, of course, and this is just a joke to provoke you all, because this idea of producing carbon credits may be an extra source of revenues, okay, which were not considered in the beginning when the first biorefineries, especially the second generation ones, were devised. And to justify the scales, I mean, if we want to do that, we need to consider from the beginning the scales that we are going to work. This is a histogram of all Brazilian sugarcane mills. This is the number of mills, or the frequency, and the processing scales. You see that the majority is around 500 tons per hour, but the new ones, which incorporate new technologies, are capable of processing 1,000 tons or even more. In these statistics are included very old and inefficient mills from the 70s, and if you filter that to the new ones, which are more efficient because they have incorporated new technologies, you see that the scales that you process is going to be even bigger. Okay, so we're talking about doing this. That's what we want to do for several reasons. And we need to do that at scales greater than 1,000 tons per hour. Okay, so that's a very important number to consider. And that's what I'm talking about. The viability limit will be extended and typical processing rates will be increased, okay, because of these new technologies. And why do you want to increase processing rates? Because you increase your revenue rates, let's say like that. Let's take the sugarcane sector in Brazil as a case study, and we already defined our industrial reference unit. Oops, here. So what are the numbers, the actual numbers that we have to work? I'm going to take 500 tons per hour, which is the average today, but this is going to be the double of that, of triple in the near future. We have already sugar mills processing more than that, and this corresponds to an area around 30,000 hectares. So the area around my biorefinery is, in average, no bigger than 30,000 hectares. And it depends on the value of the product, of your products, because if we make the same analysis regarding acacia is a kind of tree, and you can extract tannins from the bark in order to process leather and so on, also to make glue and several chemical processing. If you make the same analysis regarding acacia, this area for sugarcane corresponds to a radius of 20 to 30 kilometers. For acacia, because of the value of tannin is higher, this can extend to 100 kilometers. I mean, the area is bigger. So you have to have another agricultural model. But coming back to the sugarcane industry, that's an important issue because it means that your energy vector production, ethanol or electricity, or biofuel or electricity, is dispersed on the fields. You're never going to have a very big refinery as a petroleum refinery. So that's an important issue because if you're considering producing these energy vectors, biofuels, it's going to be a distributed production. And as I mentioned, the new plants are being commissioned in this region of the histogram. So that's our reference model. We can start by defining that our plantation area is 30,000 hectares. If we multiply that by the average productivity and so on and so forth, you have those 500 tons per hour, which has to be processed during 200 days and 24 hours a day in your sugar mill. You also have, for this number, you also have the production of 35 tons of sugar per hour or 42 cubic meters per hour of ethanol. Okay, you also have a surplus of electricity around 50 megawatts during the whole year, actually, because you burn bagasse to produce that, and you have bagasse enough for your 200 days and also for the rest of the year. You also have CO2 emissions here. This is from fermentation only. You have water input. This is an important point. You also have vinasse. Going back to the fields, when the plant grows, it extracts nutrients from the soil, NPK. And that is done at the rate of 1 ton per hour. So you're impoverishing your soil, and all these nutrients are diluted in vinasse. It ends up in the vinasse. Today we're transporting vinasse back to the fields to do what we call ferti-irrigation, but it's a highly uneconomical operation because this 1 ton is diluted in 5 or 499 cubic meters of water. So to put 1 ton of nutrients in the soil, you have to transport 499 tons of water. So it's highly uneconomical. It would be a lot cheaper just to buy these nutrients in the solid state. So if you buy 1 ton or 500 tons of nutrients, you only have to transport these 500 tons of nutrients. So those are the average numbers just to establish the scales that we have to process. We can do a lot of things with that reference industrial unit. I'm calculating some numbers regarding carbon capture and storage, just to give you an idea of the potential that these biorefineries are in terms of mitigating greenhouse effects. So let's see, what would be the potential for CO2 capture for one refinery, for one sugarcane mill? Well, if you consider fermentation 200 days, you have emission of 2 tons per hour of CO2. That's not impressive, but bagasse combustion to generate energy, which is done during the whole year, you have this potential, 89 tons of CO2 per hour. Okay, so let's disregard this number, just fixed on this one. If we find some new technology which would enable to capture this CO2 and to inject that on the underground layers, what would be the potential? One mill would be capable of storing 0.79 million tons of CO2 per year. If you multiply that by the number of mills in Brazil, roughly 450, the annual CCS potential would be 355 million tons of CO2 per year, which, compared to Brazilian annual emissions, is roughly the same, at least the same scale. So in rough, what we have today here in Brazil regarding the sugarcane sector would be able to cancel all our annual emissions. This is a very promising perspective. But let's see if how these tons of CO2, which are being produced by burning bagasse, could be captured. So those are the numbers to be stressed. The annual CCS potential of all the sugarcane sector today in Brazil and our current emissions are the same order of magnitude. Let's talk about evolving towards an integrated first generation, second generation, plus biochemicals, plus supercritical CO2 in order to generate carbon credits. And let's take a look at the conversion pathways and processes. I mean, until now, I'm just speculating. I'm just giving you some numbers which show that the potential is fantastic. But let's see if, from the technology point of view, it is feasible. It's not really dreaming. Let's compare, because I'm going back one slide. I'm talking about integrating first generation and second generation. I need to elaborate a little bit on that before talking about these conversion pathways. So just to summarize the numbers that I showed you before, spread in several slides. This is a first generation plant, which this is a plant near the frontier between São Paulo and Minas, Usina Vertente. It processes 350 tons per hour, 15 cubic meters per hour of ethanol, roughly 25 tons per hour sugar, 20 megawatts, and it processes sugarcane. And that's how much it costs. A sugar mill or a biorefinery, a first generation biorefinery, is a kind of commodity. You can sign a contract, you give the area to these industries, you give some electricity, some water for them to build, and after 1 or 2 years, they are going to give you this sugar mill operating. Okay, it's really working to that point. I mean, it's a commodity. Now let's see some numbers related to Chemtex in Crescentino. It processes 40 tons per hour today, but it is supposed to go up to 60 tons per hour. That's the original design. 16 cubic meters of ethanol, 7 megawatts of electricity, It also produces some chemical compounds, and it works with today with wheat straw, but also with arundo and agricultural residues. That's a very important point because it can process several types of biomasses. That's an improvement because our sugar mills today, they are only capable of processing sugarcane. Okay? Well, and it costs roughly $200 million. So if you have $200 million, what would you do today? Well, I would go to, to the beach, to an island, and live the rest of my life. But if you're not interested in those kind of stuff, you have to decide. Are you going to buy a first-generation plant or a second-generation plant? Now, you see, your revenues come from what? From selling energy vectors. So this one produces a lot more than this one, okay? So my point is, if you have the possibility of using first-generation conversion pathways, why are you going to buy a processing plant that is capable of using only second-generation pathways? I mean, the assumption is that you are able to use first-generation pathway. I'm just provoking you guys, those that are not sleeping yet, and bear that in mind because I'm going to elaborate on those numbers. Okay, so I need to explain what's biomass deconstruction is all about. Well, I'm going to do this very quickly, actually. I prepare a kind of animation. Let's see what's biomass. You have a plant, whatever, sugarcane or corn or acacia, and let's say that this plant has fruits or seeds, for instance, and these seeds have molecules, simple sugars that can be processed through first-generation pathways. Let's take sugarcane. Sugarcane has juice. This juice has sucrose. Sucrose can be fermented without further chemical processing. So that's what I call first-generation pathway. Now let's see the second-generation pathway, those parts of the plant that do not have those simple molecules that you can process through first-generation pathways, direct fermentation, for instance. So I'm roughly talking about the lignocellulosic part of the plant. So if we could cut a small piece of the plant, and if we could zoom on this piece, what we would see a cell, for instance, with all its internal structures, and you have the cell walls. And most of the biomass that you are interested that has a high energy content is related to these cell walls. So let's zoom in again. You have several layered meshes or several layered microfibrils. Let's zoom in again. These microfibrils are organized into other layers of fibers, okay? And let's zoom in again here. You have this, this is cellulose, which is a crystalline polymer, very regular. And if we could zoom in again, we get molecules of interest. Cellulose is all of that, and each monomer here is glucose. So if I could cut these bonds here with very tiny scissors and separate this part of the molecule, that's glucose, that's sweet. If I could put it in my mouth, it would feel a very sweet taste. And we can process this part of the molecule through first-generation pathways. I mean, yeast can ferment this kind of molecule, but cannot ferment the whole molecule, or even less, the bigger structures here. So biomass deconstruction is the process of getting those fermentable parts of the molecule. So that's what has to be done. And there's a lot of people trying to develop technologies to do that at those scales that I mentioned. There's a lot of technology that can do that by several ways, several pathways, but some are more viable, some are not. Okay, so this still has to be tested at the scales for the business, the whole business, to be viable. Okay, so the objective is to separate those molecules which can be fermented through or processed through first-generation pathways. Or integrated 1G, 2G model would be something like that. Let's suppose that we're processing corn or maize. Okay? So you harvest the seeds here in all straw and stalks and so on. So you have an industrial separation operation here, which will separate the parts of the plant that can be processed through first-generation biochemical routes. That's for corn, but that's the same for sugarcane. And what's not processable through first-generation pathway goes to second-generation pathways and also thermochemical pathway. If you have straw here, you can use part of the straw to generate energy and also chemical compounds through thermochemical pathways. I mean, in addition to combustion, you can do pyrolysis or gasification, which enables you to produce gasoline, for instance. In the Second World War, you know, the Germans produced a lot of gasoline for their Luftwaffe and the tanks and so on from coal, following a thermochemical route. But we're talking about this one, the second-generation biochemical pathway, which means, I'm going back one slide, to do all these operations here. So all these operations here are done in this, what I'm calling biochemical second-generation pathway. It enables you to produce fuel or biofuel and chemicals by saccharifying parts of the biomass that you can ferment. And what you cannot, residues, lignin for instance, you can send to the thermochemical pathway to generate energy. Zooming in those processes, that's what's being done today, the first-generation sugar mill. We have sugarcane, we have the mechanical processing, which will chop, will increase area for processing, but also it will separate straw and sand and dirt from biomass. So straw can be sent to a boiler in order to generate steam, in order to generate electricity, okay? And what is processable through the first-generation pathway, sugarcane juice, goes to fermentation, distillation, ethanol. And here you have what's not fermentable. You have bagasse that you will dewater. Bagasse here has a humidity percentage of around 80%. That's not possible. It's not possible to burn bagasse at those humidities, so you have to dewater to decrease that to 50% humidity. That's what's possible. So I'm stressing this because this operation consumes a lot of energy in the whole process. Evolving that towards an integrated first and second generation process would mean what? Would mean to include a biomass deconstruction processing pathway. So it's something like this, roughly speaking. You have some amount of bagasse and some amount of straw has to be pre-treated and then hydrolyzed in order to get sugars, fermentable sugars, to increase ethanol production. Okay? And what's not fermentable, residues, lignin, for instance, goes to our new biorefinery, our new second generation process, which will recover some chemicals to produce some chemicals in order to generate revenue, but also it will recover solids. We have solids here, solids with high energy content that can be burned to generate energy. The processes that has to be developed and included in the already existing first generation processing model. But let's go further. Let's see how this could be transformed into a CCS machine, a carbon capture and storage machine, which means that this CO2 here, that's going back to the atmosphere, it has a small greenhouse potential because this carbon was in the atmosphere in the first place, it was captured by the plant. It was not stored in the underground. So the greenhouse potential is low. But instead of emitting that to the atmosphere, we could capture and insert that in the underground. So let's see how. We would have to change my boiler technology to a technology called Oxy Fuel Combustion. Guys from Leeds and Imperial College are very advanced in those technologies. We are not here in Brazil. This Oxy Fuel Combustion technology actually takes pure oxygen to the combustion process, not air. I'm going back one slide. Here, it uses air to burn biomass, and we emit CO2 to the atmosphere. So we change that to an Oxy Fuel Combustion technology, which will take pure oxygen to combustion, which means that we have to separate O2 from its primary source, which is air. So that's an important issue of the problem because it will consume energy. If we do that, we have pure CO2 here and also some water, which we can dewater and compress in order to produce supercritical CO2. The processes that we have to develop, I'm going to show you how this can be done. But first, let's see the sensitive or disruptive technologies related to those ideas, which are we are speculating in order to see if it's possible. First of all, biorefining and upstream processes mostly focus on first-generation processes. So we need to develop more advanced biochemistry, okay? And also a very sensitive technology, the development of low-energy separation methods. Phenolmatic transporting, for instance, is some technology that we are investigating right now. Also, regarding second-generation conversion, we need to have low-energy pretreatment methods and also enzyme production for hydrolysis. That's related to the biomass deconstruction. I'm not going to elaborate on that because that's not the right place. Okay, but those are sensitive technologies. That means we have to invest on that or to look for partners in order to do that more efficiently. And also, if we want to evolve to a CCS strategy, we have to develop oxy-fuel combustion strategies. Remember, always we need to do that at those scales that I mentioned in the beginning, 500 or even more, 1,000 tons per hour of biomass processing. So we need to develop oxy-fuel boilers and also low-energy O2 separation techniques. So those are the sensitive technologies. We're going to have to focus on that. We have to develop by ourselves. We're going to have to eventually, or possibly, it's a very sensible idea to look for partners. We can benefit from complementary expertises. Okay? So let's see what's an oxy-fuel boiler. Let's start by a traditional boiler. That's a traditional boiler. You have biomass being injected here. Air is injected here. It burns. Heat is used to produce steam. Okay? And you have flue gases here in your stack. The next, that's a photo of, actually those are two boilers, not only one, from that sugar mill in near Brasilia that I mentioned. Okay, so that's the size of a boiler like that. It's very, very big. We're going to use the steam to drive a power cycle. This is the thermodynamic cycle, okay? But actually, it produces energy. That's the red arrow here. This energy is going to drive all other processes in your industry. You can sell the surplus electricity. Remember, for our reference unit, you have 50 megawatts there, in average. And everything that you need in terms of energy, you're going to draw from this red line here. So that's the first generation power cycle in a traditional mill. To transform that into an oxy-fuel boiler, what you have to do is you need some energy in order to separate oxygen from air. So you have oxygen here, you have nitrogen here, for instance. This can also be a source of revenue. So you have oxygen here, which can be used to burn biomass.
actually you cannot do that with pure oxygen, because if you do that, the combustion temperature will be so high, 5,000 degrees Celsius, so it will degrade, it will destroy completely your equipment here. So it has to be diluted with something, and actually we're going to use CO2 to dilute this oxygen, okay? Just to anticipate what's coming next. But if you burn that with oxygen and some CO2, what you have here in your flue gases is what? Is CO2 and water. Anything else? First step is to separate water, which you can do just by cooling your flue gases. Water will condense, and you have water here, some amount of water. By the way, a lot of water. You have something like 50 or 70 tons of water per hour. So it's a lot of water. It also can be a source of revenue. Remember, a first generation mill imports in average 1,000 cubic meters per hour for the processing. That's a problem today. We're trying to prove that, and a source of water could be the condensed water from the flue gases. Okay? So if you condense water, you have virtually pure CO2 here. You can use a small amount to dilute O2 in order to decrease the combustion temperature to those ranges around 500 degrees or something like that. And you have a pure flow of CO2 here. But it's gas CO2 near 170 degrees, near the atmospheric pressure. If you try to inject that in the underground, it's not possible, because it has a small amount of mass that occupies a very big volume. So it's not adequate for underground injection. What you have to do is to transform this gaseous CO2 into what we call supercritical CO2. I'm going to explain what's that. So what you have to do is a series of compression and cooling. So you have some energy that you draw from this energy line here. You compress CO2, then you cool it, compress again, cool it, compress, to achieve levels of pressure and temperature in which CO2 is said to be supercritical. A supercritical fluid actually is, you have pictures here, if you never see, I think I have another one here. Okay, yeah. Supercritical fluid is actually a fluid where the gas phase is soluble in the liquid phase. You have a kind of a mayonnaise here. If you could look at that with microscope, you have a kind of mayonnaise here. And it's very interesting because it has very good properties. It behaves more or less like a liquid. I mean, the density is very close to the density of the liquid, but the viscosity is very close to the viscosity of the gas. If you're going to inject that in a rock bed, for instance, which has pores, which has very tiny, let's say, caves, because the viscosity is so low, it will flow very fine through these pores within the rock. Okay? And because the density is so high, that means that when you do that, you're going to store a high amount or a lot of kilograms or tons of CO2 just by pumping this supercritical CO2. So it's very interesting for underground injection. And what you have to do is just make these operations here, compression and cooling, which can be done very easily. This is no big deal. This is very traditional equipment. You don't have to develop a new flying source to do that. But remember, you have to draw some amount of energy here, which means that you're going to decrease the energy that you are exporting here. You also need to have some energy to do that separation. What we're doing right now, we're making these calculations to see if what we get here is still positive, okay, in order to see if that's feasible. I want to talk a little bit about shale oil and gas, because I think it will change the whole scenario in 10 or 15 years. And still, biorefineries will play an even more important role in this scenario, because if you're going to increase your fossil CO2 emissions because it's so cheap, because shale oil and gas is so cheap, that's even more reason to have CCS machines. My whole point is that these biorefineries can play the role of CCS machines. Okay, so let me just talk about what's hydraulic fracturing techniques, and also about the environmental consequences related to the fact that this technology is still not very well tested, but it will be. And that's at least my belief. So shale actually is, let's say, fossilized mud. You have these layers of mud, which has a lot of organic material, and it fossilizes, so it's a kind of a porous rock with a lot of gas or oil, let's say, entangled in these crystalline structures regarding this rock. The problem is that it's not like a porous rock. If you drill a hole here, that doesn't mean that the gas or oil that you have is going to flow through this rock in order to get to this hole, and it's not going to do that by itself, as in a petroleum or gas reservoir. Okay. The problem is that it's so tightly entangled within this crystalline structure of the rock that you have to do something else. So that's what hydrofracturing is. You drill a hole. When you get to the shale, you continue this layer. Then you insert this kind of probe with several plugs here. And from inside this pipe, you inject a very high pressure pulse, okay, like a water hammer. This pulse will fracture parts of the rock here. So you do the pulse here, the pulse comes, it is communicated to this chamber here, let's say, and will fracture the rock. So you have a fracture here, here, and here. You can have several micro fractures which will mimic, actually, our lungs. So the idea is to increase the interfacial area to enable gas or oil that is entangled to flow through these fractures and finally to flow to the well here so you can extract. I'm going to talk about the environmental problems and also what we call the geopolitics. But let's talk a little bit about the problems. Remember, problems are opportunities, actually. If you are not able to, I'm going back one slide. If you're not able to confine all these fractures within the shale, like this, these fractures can go to water reservoirs. And the gas, let's assume it's gas, instead of flowing through the well, it's going to flow to these water reservoirs and will eventually go to a water lake or even water wells. So you have contamination. This is happening because the technology is not well tested for these purposes. Okay, this is not a new technology. It has been done for copper exploitation, for instance, in Chile. They use this technique for copper exploitation. It has been adapted to shale, but you have to test it and to solve the problems that are. You can have several types of solution. You may have a layer, impermeable layer here, which will confine gas under it. But those are the problems. Let's see the advantages. Shale, actually, the whole world has. Every country, almost every country in the world has. So it's very different from petroleum, which is confined in some few countries. Brazil has a lot in Northeast region, United States, Russia. In addition to having a lot of oil and gas, they still have shale. And also it's onshore, so it's very cheap to explore compared to offshore exploitation. There are some, I think I have a slide for that. So it's worldwide evenly distributed onshore. The hydrofracking technique enables commercial exploitation. We can assume that the problems that are being observed today will be solved in the near future. We can assume that. And there are some estimates that 35% of world oil and gas supply will come from shale oil and gas. Prices will drop because of that, because you have an increased offer to 25 to 40%, which means that, for instance, our pre-salt exploitation will be endangered because of oil prices. It may be a very big mistake that we made by investing on pre-salt oil instead of investing in shale oil and gas. Concluding, the scenario is changing, okay? We don't know how it's going to change. Maybe the shale oil and gas exploitation will represent an even stronger drive for efficiency and low cost regarding biorefineries, not only biorefineries, but all other sources of renewable energy. This is a problem, but also a very good opportunity for new technologies, more efficient technologies. Regarding CO2 emissions, biorefineries can play the role of sun-driven CCS machines. So it's not only displacing fossil energies, but also recapturing CO2 in order to inject that underground. And this is still speculation. A carbon-neutral economy could be something like that, because these sources, although non-renewable sources, but because they are so cheap, we're not going to avoid their exploitation. This is going to be possibly increased, and we are going to increase fossil CO2 emissions. The idea is to devise these CCS machines so CO2 can be captured by plants, which are essentially what I call sun-driven CCS machines, because basically it converts solar energy into chemicals which contain energy from sun. And this biomass can be used to produce energy, biochemicals, and so on. If the amount of energy necessary for supercritical CO2 production is smaller than the amount of energy that I can produce, we can re-inject the CO2 here and have a neutral effect. Okay? I try to elaborate on the technology challenges related to this. And, well, I hope you had a good time. Thank you very much. Quer fazer a discussão? Você que sabe. Agora que vem a sua aula, o que é o programa aí?